So now we come to the famous equation, and of course we're referring to E equals mc squared. You may remember that Einstein's paper on the special theory of relativity in 1905 was published in June. A few months after that, he published a short note in September, essentially saying, remember that paper I published a few months ago? Well, I've been thinking more about some of the things contained in it, some of the implications, and discovered a very interesting relationship. And that relationship essentially was E equals mc squared. Now, unfortunately, to really understand this, to derive it in a sense, even sort of in a hand-waving sense, would require us to spend a couple weeks on concepts of energy and momentum and a few things like that. So we don't have time to do that, but want to just review a few key things about it and bring out a few of the key concepts as well. And we're going to start with a concept of kinetic energy. All the way back in the 1700s, early 1700s, scientists, they weren't really scientists at that time, they were called natural philosophers, were investigating things with how objects move and collisions and things like that, and had identified a certain quantity that seemed to be very important. And over time, in the 1700s into the 1800s, this quantity was came to be known as kinetic energy and had the form of 1/2 mv squared, where m is a mass. So you could imagine a particle, a ball, tennis ball, something like that, mass. And then v is velocity. Okay, so we're not talking relativity here. We're just talking everyday type of velocities. And also, along the way, as this developed, especially in the middle of the 1800s, mid-19th century, the idea of conservation of energy came about, that there were different forms of energy, and you could transform one form of energy into another form of energy. And so they developed those concepts a little bit more as well. And one key thing about this was that they really focused on things like kinetic energy. And what happened when Einstein came along in 1905 and came up with this idea that energy, okay, of course, here's the famous equation, E equals mc squared. So we see, just compared to this equation for kinetic energy, mass is involved, and there's a velocity squared involved in each case. This is just the regular velocity of an object. This is obviously velocity of light. So there's some similarity between them there. But really what Einstein discovered was not quite this equation. This is a special form of the equation he really discovered. What he discovered was, and we're going to come back to see how it relates to conservation of energy here in a minute, he discovered this, that energy is gamma mc squared. Okay, gamma mc squared. In other words, here's our familiar Lorentz factor coming into play here. And if we play around with this a minute, let's just remember back when we were talking about the Michelson-Morley experiment, we used something called the binomial expansion. So we're going to bring it out of our toolbox one more time here. And remember, it's this, that if you have something 1 plus x to the n, some quantity x to the n power, if x here is much less than 1, then we can write this as 1 plus nx, approximately, with that. So we're going to exploit that here because, of course, gamma, so what we have here is gamma in our one form, 1 squared of 1 minus v squared over c squared there. But let's write that in a slightly different form, as we've done before. We haven't done this recently, but before we could write it like this. We have 1 minus v squared over c squared to the minus 1/2 power, so that's just gamma. Oops, I forgot the mc squared in here, so we'll put that on the top. Okay, mc squared over that. So that's this times mc squared. So again, this is just gamma right here, times mc squared. And note that this has the form of this because, especially if v is much less than c. So if our velocity is much less than the speed of light. And what do we mean by much less? Well, even up to speeds like 1/10 the speed of light. V squared over c squared is still going to be a very small value. So we'll be able to expand this out and put it in this form here using our binomial expansion. So if we do that, what this happens here is we've got Okay, here's the exponent. The minus 1/2 is equivalent to the n there. And I've got a minus here instead of a plus, but it works the same way. So essentially I'm going to have, for this part right here, this becomes 1 minus, and then the minus 1/2, and then v squared over c squared, and times mc squared. Okay, now remember, this is an approximation for when v is much less than c. So up to about 1/10 the speed of light, someplace in that region. So still pretty fast compared to our normal everyday experience. And so note we've got a minus times the negative 1/2, so that becomes a plus 1/2. And so we'll write this out one more time here. So we got 1 plus 1/2 v squared over c squared times mc squared. Now we're going to bring it back over here in a minute here just to look at it a little bit better. Okay, so this is how we got there. Let's erase this part now and say, okay, so we've shown that gamma mc squared can be written as, we'll rewrite this here, 1 plus 1/2 v squared over c squared times mc squared if, we'll just say if v is less than about 0.1 c, something like that, for low velocities, in other words. But let's look at this a minute. Look at what we've got here. 1 times mc squared, that's just equals mc squared. Then I've got 1/2 v squared over c squared times mc squared. Well, the c squareds here cancel, and I'm left with plus 1/2 mv squared. That is kinetic energy. So that falls right out of this general formula for in the low velocity limit. Well, what is this telling us? Back before Einstein came along, people would look at kinetic energy and other forms of energy, and would talk about the conservation of energy. What Einstein is saying with this formula is that there's another form of energy right here, too. It's not only the kinetic energy that's important, but this mc squared factor as well. And note that if we just have v equals 0 here, then energy just is mc squared. We get the famous form of the equation, E equals mc squared here. But what this is really saying, going back to conservation of energy, is that before Einstein came along with this equation, then the idea was, well, sure, you'd have a conservation of kinetic energy. It could go into other forms of energy as well. But no one really paid attention to the masses involved. And what Einstein is saying, you know what? You've got the masses involved maybe in something, and you've got some energy involved. You can actually convert in between them and still have the whole thing be conserved. Okay, so that's what the implication of this equation is, that in principle, you can take some of the mass energy here, in a sense, sometimes called the rest mass or rest energy, because if v is 0, you're just left with the mc squared part here. You could potentially convert some of this into kinetic energy, or you could go the other way as well. As long as if you convert some of this, it turns to this. If you have some of that, you can turn to that. As long as energy itself, the total, is conserved, does not change. And again, we don't have time, unfortunately, to go into all the details of this. But essentially, what you get out of this, what it leads to eventually, are things like nuclear fission and nuclear fusion. Fission and fusion. So the idea here, fission and fusion. The idea is you can turn some just ordinary mass, it's like it has energy locked up inside of it. It's really a form of energy. If somehow you can liberate that energy, you can turn that mass directly into things like kinetic energy. And it turns out, in the atomic realm, really the nucleus of atoms, where the protons and neutrons are, that if you turn, say, if you have certain types of uranium, the uranium nucleus can split apart, and it turns out that if you add up the components that are left, say, to make it simple, say it splits into 2 pieces, versus the original uranium atom, the new atoms, the smaller constituents there, have less mass than the uranium atom did. And therefore, where does that missing mass go? It turns into energy. And that's really the idea of nuclear fission, that you can split apart certain atoms, certain nuclei, and that releases the mass energy, in a sense, that's stored inside there. Nuclear fusion goes the other way. It turns out that for lighter elements, say hydrogen, the lightest element, if you fuse two hydrogen nuclei together to create a helium nucleus, a few other things involved there as well, but if you create a helium nucleus out of it, then, and you look at it, the helium nucleus actually has less mass than the two hydrogen nuclei that you use to put it together with. So again, where did the missing mass go? It turns into energy. And that's the whole idea of nuclear fusion. You're fusing nuclei together in a sense. And this is how the sun works, for example. So we're all here because of the sun, in a sense. And so we're here because of nuclear fusion. Nuclear fission was developed, the idea of it, the concept of it, over a number of years, 1920s, 1930s, ended up development of the atomic bomb, or atomic energy in general. In other words, when you're liberating energy like this, and if you think about it, because c squared is such a big number, it takes just a little bit of mass. If you can liberate the energy inside there, you get a lot of kinetic energy and heat energy and other forms of energy out of that. In fact, just to give you a glimpse of it, we all sort of have a general idea of the destructive power of an atomic bomb. It doesn't take a relatively small bomb to level a city, and things like hydrogen bombs, which are based on nuclear fusion, actually have even more power than that. But in terms of more peaceful uses of it, for example, if somehow you could liberate all the energy contained in a mass of just 3 kilograms, okay, so that's, not much mass there. If you could do that, if you could turn that all into energy, you could power a city with 100,000 inhabitants for 100 years. Okay? A city of that size, 100,000 inhabitants, is needs a generating station, electrical generating station, of about 100 megawatts, 100 million watts. And therefore, just 3 kilograms of matter, again, if you could liberate all the energy inside there, would power a city for up to 100 years. Now, in nuclear fission and nuclear fusion, you're just liberating tiny amounts of the mass energy available, but you're getting a lot of energy out of it, even in those cases. Now, you might ask, also going back to Einstein, what was his role in especially the atomic bomb? Because you may know that he wrote a famous letter to President Roosevelt, Franklin Roosevelt, in the United States, alerting the president of the fact that scientists had recently discovered nuclear fission, actually, so this was in the early 1930s, right around 1930, and the possibility of either a controlled nuclear reaction or even an uncontrolled nuclear reaction using nuclear fission that would release incredible amounts of energy in a bomb was feasible. So beyond that, though, Einstein really didn't play much role in the development of it. He was asked to write the letter by some of the other scientists involved who were very concerned about this. And because his name had cachet, as it were, he could get the attention of the powers that be. They approached him to write the letter. But beyond that letter, he really played no role at all in the development of the atomic bomb and the Manhattan Project during World War II in the United States. So that's Einstein's role in it. Certainly, in a sense, it all does go back to the E equals mc squared equation, the idea that there's an incredible amount of energy stored in regular, ordinary matter if we can liberate it in some sense there. One other point to make here about equals mc squared, gamma mc squared, and the like, is that we've talked before about invariance and the fact that really a better name for perhaps the special theory of relativity would be not the theory of relativity, but the theory of invariance, because one of the key invariant quantities is the speed of light. Or actually, technically, it's the speed of massless particles, but we'll just say the speed of light, invariant, no matter how you're moving with respect to somebody else in respect to a light beam, you will always measure the speed of light to have the value c. So we talk about invariance. And turns out that in 1918, so just a few years after the miracle year of 1905, and even just a couple years after Einstein introduced his general theory of relativity, a mathematician named M.E. Noether, whom Einstein considered one of the greatest mathematicians ever, she published a very famous theorem that essentially tied invariance in to this idea of conservation of energy. And she was able to show that other quantities, like if you think about just if we move from here to there, that doesn't change the laws of physics. That's called translational invariance. So we can talk about translational invariance. That if I move from here to there, and I do the same experiment, if I do an experiment here, do an experiment there, I shouldn't get anything different in terms of my answers, assuming everything else is equal there. In other words, where you do the experiment in the universe shouldn't matter, again, assuming the other conditions are equivalent. So that's translational invariance. And out of that, Noether showed that the concept of conservational momentum came out of that. Again, momentum is beyond our course, but just the idea of translational invariance is connected up with this idea of conservation of some quantity, in this case, conservation of momentum. Another idea is rotational invariance. As I turn from side to side here, or point in that direction versus that direction, maybe versus that direction, I should get the same results. So that I have rotational invariance of the laws of physics in some very general sense. And that leads to the concept of conservation of angular momentum. In other words, Noether showed that these were equivalent concepts. If you have rotational invariance, you get conservation of angular momentum. And then finally, related back to conservation of energy, she showed if you have invariance through time, so time-like invariance in a sense, that connects directly with the idea of conservation of energy. So if the laws of physics are the same through time, and of course time and space-time are the key concepts underlying the special theory of relativity and later the general theory of relativity, Noether showed that the concept of time and moving through time, whether I do an experiment now or 10 minutes from now or 2 years from now, again, other things being equal, that leads directly to energy being conserved. Okay? So in a really deep sense, this all hangs together. If you really start pushing it down in the depths of some of these concepts, you see that we're not just talking about sort of time dilation and things like that, but we're talking about the foundations of the universe itself and how it's put together and how it works. So those are just a few words about, again, probably the famous equation, most famous equation, equals mc squared. Again, the real form of it coming out of relativity is equals gamma mc squared, and we show that out of that you can sort of get the regular form of kinetic energy, but you really then learn about this concept, or see this concept that mass itself has energy stored in it, that mass, matter, and energy are equivalent in some sense and can be turned from one form into another, and then in cases of like nuclear fission and nuclear fusion, release huge amounts of energy potentially.